Great.
So let's start the second half of the session, and it is always my great pleasure to introduce Rachel Street, who's a longtime friend and a very close colleague. Rachel and I have been chairing the Transient and Variable Star Science collaboration for a few years, and Rachel hails from the Las Cumbres Observatory, where she runs the Microlensing program. Rachel, take it away.
Thank you very much, Fed, and hi, everybody. So thank you very much for the opportunity to speak. And I'd like to take this occasion to thank the organizers for making it possible to participate so well in this meeting. You've really shown how it's possible. Before I go any further, all of the work that I'm about to present is obviously a team effort. So allow me to credit my collaborators within the Omega project team, as well as the microlensing group within the Rubin TVS science collaboration. Moving the slide. Okay, so I'm grateful to the other speakers in this sessions for their excellent overviews of microlensing and the discoveries that Rubin is going to make. So to recap very briefly, the events will be discoverable across the entire sky, rather than a small region in the galactic bulge as was historically true. And that'll give us a much more complete view of the hidden populations across the Milky Way in different stellar environments. The events will include planetary, brown dwarf, stellar binaries, and compact objects, including low-mass isolated black holes. And there's a tremendous overlap with the Roman exoplanet survey of the galactic bulge, which will be contemporaneous with the Rubin survey, and the data will be highly complementary. So Rubin's observing strategy for LSST is in the process of being decided, as you heard earlier. The original survey strategy generally avoided the galactic plane entirely. Well, not entirely, but mostly. And that's where microlensing events were most numerous. But the project has been very good about soliciting community input several times, and numerous authors advocated for increasing the number of survey visits to the galactic plane, the bulge, and the Magellanic Clouds, to serve science drivers that ranged everywhere from microlensing to young stellar objects to galactic structure. And in response to that feedback, the latest realizations of this baseline survey strategy does now include the central galactic plane, the bulge, and the Magellanic Clouds in part of the Wide Vast Deep survey. Some optimization does remain to be done. For example, although we want to focus a lot of time on the central plane, it's also very important for microlensing to sample different lines of sight at greater range of galactic longitudes, as that gives us more insight into the population in those regions as a comparison to the central galactic plane. And they have not been previously studied intensively for microlensing before. So many of the other science drivers that we've raised also range in the sky regions of special interest that they'd like to consider. So if you take all of those regions of scientific interest for all of the different science cases and you superimpose them, as I have in this map, you can use that to then identify the regions of highest priority for surveying in the galactic plane. And we're in the process of using this to help us refine the Rubin footprint within the galactic plane. However, my key takeaway here is that really the typical survey cadence that Rubin will achieve. The sky plot on the right here shows the average gap between sequential observations during the 10-year baseline survey. And you can see that the typical gap is around 3 days. That's considering all filters combined. And the survey will typically cycle between filters. So that implies that the gap between data points in the light curve of a single filter is going to be much longer. And that cadence is significantly lower than that for traditional microlensing surveys, which usually aimed to deliver observations several times a night, as for example, the OGLE and MOA surveys. Oops. Sorry, I'm going backwards here, 1 second. Okay, there we go. So when you compare the gaps in the coverage with the key microlens features in a microlensing light curve, you can clearly see the need of follow-up observations. This example shows a stellar, and in this case, a binary lens event with a critical light curve feature known as acoustic crossing. But it also has secondary features caused by parallax signatures and other second order effects that won't be sampled by Rubin data alone. In addition to the high cadence time series photometry, we also usually need high-band multiband photometry or spectroscopy to measure the properties of the source star. And we also use high-resolution imaging both at the time of the event and several years later in order to search for signs of flux from the lens, which can be very helpful in breaking model degeneracies. Lensing by stellar mass black holes and other compact objects generally takes place on much longer timescales, from months to years. So the photometry from even a low cadence survey is sufficient to constrain the event. But I want to emphasize that it does have to be regular cadence and maintained for years at a time, since the events exhibit this sinusoidal feature associated with the parallax signature. And for Rubin, this has been important when considering the survey strategy implementations, for example, for the rolling cadences, because the cadence would have limited seasons of high cadence, but then separated by multi-month gaps. So that's something that our group has been exploring. So what do we need to follow up microlensing events from Rubin? Well, step one, of course, is to be able to identify them in real time from the alert stream. At first, there was some skepticism in the microlensing community that a survey with a cadence of only 3 days could reliably detect microlensing in progress, as opposed to simply recovering them after the event is finished. But several lines of work have now dispelled that skepticism. The first systematic microlensing survey from a wide angle but low cadence really came from Gaia in 2015. And I won't say too much about that because of we've just had an excellent talk from Wukesh, but the survey has produced a reliable feed of over 400 microlensing alerts from that time. Daniel Godinez developed a random forest classification algorithm and used it to explore whether he could recover simulated microlensing events in low cadence data if the survey photometry were drip fed to the algorithm as if it were arriving in real time. He used some public data from OGLE-3, PTF and the early ZTF data, and he found he was able to identify microlensing events before the peak. A key factor, though, was found to have at least 1 year's baseline data prior to the event, which helps us to distinguish from other classes of variability, such as CVs. And that emphasizes the key role that will be played by early time observations. Then as ZTF really hit its stride, Czemek Mroz developed a neural network-based classifiers for both single and binary lens events, which he's tested on OGLE and ZTF data. And he very kindly makes this data table of alerts available from the public ZTF data in real time. And one of the goals of the ZTF public surveys was to stimulate pathfinder studies for LSST by giving the community the opportunity to build systems that can accommodate the incoming data rate and to gain experience with using them. So to that end, we undertook the Omega project, which was designed to follow up microlensing alerts from low cadence surveys in particular, starting with ZTF and the Gaia mission. This project is led by Etienne Bachelet, and it was awarded key project status on Las Cumbres Observatory just as the pandemic started in 2020. Omega is designed to operate from within the ecosystem of LSST, with alerts on targets of interest retrieved from the alert brokers automatically by a TOM system, which then orchestrates a program of follow-up observations. For Omega, the TOM system is the microlensing online platform, or MOP, which Etienne built using the TOM toolkit. But unlike other programs, he designed it to operate in a fully automatic workflow where the entire program is run robotically. Now, one of the challenges that the microlensing field faces is that there's no single broker providing access to alerts from many different surveys. Instead, while he was building MOP, we found that we needed to implement a range of bespoke interfaces to each survey in order to gain access to the public data products. And most of these interfaces at the moment are not brokers in the usual sense of the term, and they're not scalable to LSST scale datasets. The most technically advanced is probably the Gaia Alerts website, which provides tabulated data, including alert classification information. So we have a routine which scrapes that tabular information and selects out targets with the microlensing label. We took a similar approach to harvest the assassin microlensing candidates from a website at Ohio State, because although assassin does push alerts to TNS, those don't include the microlensing alert classification data. The MOA survey that was mentioned earlier has, of course, been providing microlensing alerts to the community for over 25 years now, I believe. So we had existing software to access their website. And CTF discovery data are, of course, being disseminated via a Kafka stream to all of the public brokers. However, the identification of microlensing events from this stream is operated somewhat independently of the brokers by Przemek Moroz himself. And as a collaborator in Omega, he provided us access with the tabular information directly. So that highlights an important point. The broker ecosystem is under rapid development, and we are in something of a transition phase from older alert handling mechanisms. And that transition is happening faster in some science topics than in others. Of course, the interfaces to the APIs for the brokers are already available from the TOM toolkit, but we can't always use them if the classification information provided doesn't include the type of variability that the user is looking for. So working to broaden the classification data that the brokers produce to include a wider range of science will strongly enhance the science return from LSST. I do want to mention some ongoing developments that are very relevant here. The first is that the team of the Think broker has collaborated with Etienne and Daniel Godinez to implement the Microlea algorithm to classify CTF alerts. So they are producing microlensing candidates, and we're in the process of switching over to use Think. I also want to note that the RAPID algorithm developed by Daniel Murat-Krismer recognizes microlensing as one of its wide range of classifications. And I understand that the team of Antares is working to incorporate that as a feed. Moving on to target selection, having gathered this list of microlensing alert, MOP then needs to provide automated modeling of the light curve data for all of the targets at regular intervals in order to fit up-to-date microlensing event parameters, which is done using Etienne's modeling code Philema. The resulting parameters are then used to prioritize targets for follow-up observations. The algorithm evaluates how sensitive each event is to perturbations in the microlensing light curve caused by binary companions at each stage of the event. That allows us to prioritize the targets where additional observations would be most valuable to constrain the event light curve. And that's done on a real-time basis, with targets being prioritized if additional data within the next 24 hours would help us to distinguish between models. And that takes into account various observational constraints as well. This stage of the workflow is also fully automatic, and it's a deterministic process. And that is terrific because it means that the selection biases can be fully characterized. Furthermore, the output of the process is not just a list of targets to observe, but also descriptions of what the most valuable observations would be in order to characterize those targets. The observations are then submitted automatically. The Omega program uses the LCO telescopes, of course, but the TOM package provides interfaces to a range of other telescopes as well. For microlensing, the most important time for observations is around the peak of the event, but we need observations in the wings as well to constrain parallax and other second-order effects. So Omega automatically recognizes two different modes of observation. It does observations in the wing as standard Q mode, and we use rapid response time reserved only for high priority events that are very close to the peak. or where there's an anomaly has been detected in the light curve. Once the reductions are carried out, the resulting data products are downloaded automatically for reduction. The instrumental signatures are removed with LCO's in-house pipelines, after which we perform difference image analysis using our PyDan-DIA package. That pipeline is actually integrated with the TOM system so that it automatically uploads the resulting light curves to MOP as soon as they're available. And that then enables the updated light curve to be remodeled and refitted as promptly as possible. And that gives us the opportunity to respond to anomalous features in the light curve. So to give an example of this workflow operating in the real world, I'd like to share the process of us responding to the alert for Gaia 21AUW. This shows a screenshot from the map platform shortly after the candidate was discovered by the Gaia mission on the 16th of February last year. MOP received the candidate automatically shortly after it was published on the Gaia Alerts Index, and it matched it with catalogue data available from ZTF. As early modelling of the event suggested that it would reach a bright and highly magnified peak, it was selected as a priority target, and MOP submitted the first observing request for it at 16:02. And that's because our scheduling program was designed to run every 4 hours. The first data of the observations came through within hours of the alert being issued, and then MOP continued to monitor the event through until October the 6th of that year, so for about 8 months. And during that process, it automatically adjusted the observation parameters such as exposure time and cadence to suit the different phases of the event. This plot shows the resulting dataset in a model produced by Chris Rabicki. The Gaia data are in red, and you can see the LCO data shown in dark blue. Following some recent upgrades, the PyLima package can now combine both the astrometric and photometric data from Earth and space-based observatories to constrain the event. And in a relatively long timescale event like this one, you can clearly see the space parallax signature that results from the different lines of sight to the event from the separated observing platform. And that helps us to break the degeneracies in the model. So we've demonstrated then that fully automated follow-up programs are possible, and they have the advantage of selection criteria that can be well characterized. And that's a great help when you're trying to back out the underlying population distribution. The broker ecosystem is rapidly developing, so we have learned that we need to keep the maintenance of our interfaces up to date to ensure that we can take advantage of current functionality. But it seems that not all categories of variability are well served by this ecosystem yet. And this is something I noticed that the broker teams have requested community assistance in providing more detailed classifications, especially for variable style types. And I think distinguishing transient events depends on our ability to eliminate other classes of variability. So improving that will benefit everybody. We heard earlier in the meeting that there are teams that are interested in exchanging information between TOM systems, and we are certainly not the only team that is interested in following microlensing discoveries. Several other teams are also using TOM systems, notably the black hole TOM that you just heard about from WooCache. And as Danny highlighted on Tuesday, there's a danger of bunch ball, where all of the teams rush after a select few tiny discoveries and then end up neglecting all of the others. So here again, enabling coordination of our follow-up efforts is clearly something that can improve the efficiency of those efforts and expand the range of discoveries that get properly characterized. Earlier in the meeting, we heard about one approach to addressing this issue with the Hermes system. And I think it's a great idea, especially if it's broadened out to include a wide range of types of variability. We're also exploring other options to enable TOM systems to send information direct to other pre-authorized TOM systems. That's something that has been prototyped previously, but obviously it does raise some questions about access and permissions control. So this is something that is high on the list of priorities for development. Of course, one major difference between the current surveys and LSST follow-up is going to be the magnitude range of discoveries. Rubin will probe fainter with a single exposure to detections between 16th to up to 25th magnitude. Following those discoveries is obviously going to require telescope time on bigger glass. But we still need those facilities to support flexible Q-mode observations that are time domain friendly, such as rapid response observations or long-term monitoring. And we need them to be able to allow requests to be submitted programmatically, as that makes the follow-up programs so much more efficient. The AON network goes some ways to tackling this issue. This is a partnership between LCO and NOIRLab, Gemini, and SOAR telescopes. And it makes all of those telescopes available in this time domain friendly scheduling. Now that's a good start, but we're going to need time on many more facilities, both not just for telescope time itself, but also to make additional instrumentation available. So we hope that this network will be very much enhanced in the near future as a result of the Rubin program of in-kind contributions. Several contributions did contribute telescope time on a range of different facilities, and we're working to make those facilities programmatically accessible. That's going to be the subject of a special session at the upcoming Rubin Project and Community Workshop. So I'd like to wrap up by reiterating that preparations for microlensing with LSST are gathering pace, thanks to numerous contributors, especially within the Rubin Science collaborations. We've been exploring many of the key practical aspects necessary to both enhance the survey's observing strategy so that it maximizes the number of detections, and also to develop the tools necessary for us to coordinate the follow-up of those discoveries. That experience has taught us that we face many of the same challenges that other transient observers are reporting. So again, I'll emphasize that taking the broad view of astrophysics whenever we develop systems and tools for Rubin science, it's much better to develop a system that can serve a range of science goals than have everybody reinvent the wheel in several different subframes. We'll stop there. Thank you very much for your time.
Thank you, Rachel. Thank you for a very detailed and extremely clear talk. Do we have questions? I had to say, you left me with no questions because of the clarity of your talk, but I do have one actually, as always. So if you had to choose one thing, if you had to choose one thing that Rubin should focus on to improve the survey strategy, what would that be?
I could be selfish and simply say spend more time in the galactic plane, but I recognize that we need to balance the science needs of a wide range of surveys. I think we can do that. But like
number of observations would be like really just more time, not any specific tweaking of the cadence. You would choose more time over any specific tweaking of the cadence.
I would love to get more time. However, I think we can be more clever with how we distribute those visits. And we can be more judicious to make sure that those regions which will really benefit from having high cadence get the high cadence. And we don't neglect the rest of the galactic plane and make sure we get coverage even at lower cadence where we can still get a great deal of science out. I know that's a hard balance to do, but I feel we can do it.
Thank you. And Gautam has a question.
Thanks, Rachel. This was a great talk. We've heard over the past week about all of these efforts to connect different TOM systems, things like Hermes, and pass information between different observatories for follow-up. But it strikes me that we don't have a unified taxonomy yet where we can really have every party know that when somebody says this is a binary microlensing object, that can be interpreted by another group also as a binary microlensing object instead of some bit mask that says this is a type 1a supernova. And I was just wondering how LCO and you, with your experience in setting up these standard systems for communication, might go about trying to address that.
Well, in fact, microlensing as a field did have such a clearinghouse type system. It's called Artemis. I think the technology behind that system needs a revamp for the LSST era, but the same principle can be applied. And I think that a tool like similar to the Hermes system can achieve that. Generally, when somebody detects an anomaly, we've in microlensing, we've got that down to a fine art. We do broadcast that information. Currently, it's broadcast by email mostly. And I think just replacing an ad hoc email service with something like Hermes, we can address that issue.
Thank you again, Rachel. Let's thank the speaker
Thank
one
you
more
all.
time. And our next speaker in the